and we transition to the next paper, increasing input accuracy of embodied devices via electrical muscle stimulation, from Tony Chen from the University of Chicago.
Hi, my name is Lonnie Chen, and today I will present our work on embodied devices. And this work was done in collaboration with my colleagues Yudai Tanaka, Nora Amin, Jazz Brooks, and my master's advisor, Pedro Lopes at the University of Chicago. So we live in this world in HCI, which gestural interfaces have really taken by storm. And we have early works like Myron Kruger's Video Place, which started with simple cameras and figure detection to pave the way for more sophisticated systems, like Kinect, to control video games using gestures. And today, even watches contain accelerometers to enable gestural interfaces. And collectively, these works represent a revolution of controlling computers with the body. But you'll notice something on this slide, which is that these are all gestures as input, which is only one side of the equation. So, researchers have pushed this interaction type towards gestures as both input and output. We first explored this with mechanical actuators, and then exoskeletons, and also searched for a means of miniaturization by means of electrical muscle stimulation. And these devices actually provided something really wild, which is that you can control a computer, both input and output, with your body alone, just using gestures without sounds or visuals. And we call these systems embodied devices. You input by using gestures, by moving your body, and for output, embodied devices move your body. Unfortunately, designing interactions for embodied devices comes with its own set of challenges. So let's see an example where gestures as I/O is breaking down. And here I am listening to music, and I can control the volume using a simple gestural interface. But I can't hold my hand here forever, so I dismiss the interface by tapping my thumb, and I go do something else. But when I return, you'll notice that the angle of my wrist no longer matches the previously selected volume. So, when I re-invoke the interface, the volume instantly jumps. It surprises me. This is an example of an inconsistency when using embodied devices. When I return to the interface, my body's pose no longer matches the pose from when I dismissed. And this inconsistency led to an incorrect input, which ultimately harms input accuracy. So, how do we solve these inconsistencies? The goal is to enforce alignment between the user's body and the underlying interface state. Electrical muscle stimulation enables us to do just that by physically moving the user's limbs. The first problem arises at the very moment of invocation. Since the user's pose is constantly changing, it is unlikely to reflect the system's state at this moment. In our previous example, this caused a sudden jump in the volume. So let's go back to our user. This time, when they invoke the interface, we use electrical muscle stimulation to automatically move their wrist to the current volume. This allows the user to smoothly adjust the volume without jumps. In fact, this supports one of Jacob Nielsen's usability heuristics, recognition rather than recall. And I find this really interesting because I think we often design emergent interfaces without considering that these long-standing, time-tested pieces of UI knowledge, like Nielsen's usability heuristics, also apply to totally new domains. Our second technique is confirmation. Without relying on visual or audio cues, embodied devices need to proprioceptively signal interface state transitions. Now, with recall, the user was able to make a smooth adjustment. But let's see how they still make erroneous inputs. Without any proprioceptive confirmation cue to signal state transitions, the user did not realize when the volume decreased. So, using electrical muscle stimulation, we delivered detents to confirm the user's inputs. As the user's wrist position crosses certain thresholds, mapping to different volume changes, these detents cause small movements opposing the direction of the movement. So this time, the user actually felt the changes as their arm moved. So they can fix the erroneous input and properly dismiss the interface. With confirmation, embodied devices can thereby support another of Nielsen's usability heuristics, which is visibility of system status. Our third and final interaction technique is called constraint. Users can perform a wide range of gestures with large ranges of motion, and sometimes an interface may need to forbid certain inputs, or simply cannot support unlimited interface states. In our case, when a user increases the volume of their music to the maximum level, the interface needs to let the user know that they have reached the max volume, and prevent their body from reflecting an invalid input state. To achieve this with electrical muscle stimulation, we constrain the user's wrist angle to the set of valid inputs in a valid range. For instance, if it exceeds the range, then with muscle stimulation, the interface moves it back into the valid range. And constraint supports yet another of Jacob Nielsen's usability heuristics, which is error prevention. Next, before I show a simple implementation of an embodied device, in fact, the one that we used in our user study to validate these techniques, I want to stress that these interaction techniques are agnostic to any specific technology. You could achieve the same thing with any sensor or actuation device that moves the user's body. For input, we used a media pipe to track the angle between the user's elbow, wrist joint, and finger joint, which is highlighted in pink. The user can tilt the wrist up and down to increase and decrease the slider. And again, note that you could achieve the same thing using wearable sensors, such as accelerometers. For output, via electrical muscle stimulation, we placed 2 electrodes atop the extensor digitorum and 2 more atop the flexor digitorum superficialis. Then we define a target angle, and we used a PID controller to stimulate the wrist towards that target angle. To validate whether these interaction techniques increase users' input accuracy, we conducted a user study. The task was a modified passive joint position reproduction test, which they did blindfolded. It consisted of 3 phases, which were demonstration, distraction, and input. For the demonstration phase, we defined 2 target wrist positions, which were a last position and a new position. After the participant invoked the system, the experimenter passively moved the participant's wrist from the last position to the new position. Then the distraction task was 30 seconds of typing sentences on a keyboard. And then finally, for the input phase, participants actively, on their own, had to reproduce the last position and adjust to the new position. Participants performed the task under 5 conditions. First, a baseline with no electrical muscle stimulation, with recall on its own, confirmation only, constraint only, and under a combination of all 3 techniques. We found that the combination of all 3 techniques together significantly reduced input error compared to baseline by about 40%. Moreover, participants rated their confidence in their inputs 30% higher than baseline under the combined condition. And these results actually suggest synergistic benefits of the techniques, since no technique in isolation greatly increased the input accuracy. First, embodied devices offer a new class of devices that could excel at extreme scenarios, such as eyes and ears free. And although I focused on extreme cases of completely muscle-based interactions, I'd argue that we're seeing a whole new generation of these pop up. Second, I focused narrowly on an embodied slider because I wanted to see if these techniques could improve input accuracy, and it did. In our short user study, untrained, inexperienced users who are not using embodied devices every day experienced a 40% increase in their accuracy. But that also begs the question of what other embodied devices are there? What if we extended these principles to other common GUI elements like toggles, checkboxes, or even radio buttons? Perhaps checkboxes could use recall to reflect multiple on and off states by flexing corresponding fingers, for instance, recording ingredients in a busy restaurant scenario. Or radio buttons could reflect the mutually exclusive nature of options by constraining the user to flex one finger at a time, such as for selecting a playback speed of your podcast. I hope that these interaction techniques will be treated as design guidelines for future embodied devices. And with that, I thank you for listening.